Let's define negative exponents by looking at a couple of examples before we set down the rule. In this first quotient here, if I write this out in factored form or expanded notation, x to the fourth power is x times itself 4 times. X to the sixth power is 6 x's multiplied by themselves. And if we simplify this expression, anytime we have a term over itself, it's equal to 1. Each one of these with division, x divided by x is equal to 1, leaving a series of 1's multiplied together in the numerator and in the denominator, x times x, or we can express it as x to the power of 2. If we use our quotient rule for exponents and subtract the exponents of common bases, which we have here, this would result in the exponent in the numerator minus the exponent in the denominator, giving us x to the negative 2 power when we simplify. Both of these were the same problem, giving us different versions of an equivalent answer. 1 over x to the second is the same as what we ended up with here. We can conclude that these are equivalent expressions, which leads us to the form of negative exponents. For any real number a that is non-zero in any integer n, if we have a to the negative n, it is equal to 1 over a to the n power. And we saw that illustrated here. We had x to a negative exponent, finding that it was equivalent to 1 over x to the second power. Dropping that quantity to the denominator made the exponent positive. And this is the negative exponents rule that we'll use then to express the following examples with positive exponents. So here we have the base 2 to a negative 4 exponential power. To eliminate that negative, we will drop it into the denominator. Same base, 2, now the positive power, and they're asking if we can simplify to do so. 2 to the fourth power is 4 2's multiplied together. 2 times 2 is 4, times 2 is 8. 8 times 2 is 16. So 2 to the negative fourth is equivalent to 1/16. In this next example, we have a to the negative third power, or a negative 3 exponent. To express this using positive, we'll use the negative exponents relationship here for an equivalent expression, which will be 1 over a to the third power. No longer do we have that negative exponent, but we have an equivalent expression. In these next two examples, illustrating what is being raised to the power, here negative 4 is in parentheses, so it is that quantity. We're treating that as our base raised to the negative 2, which, using our negative exponential relationship, the negative can be replaced by taking that base, in this case negative 4, to the denominator, and now with a positive 2 exponent. Simplifying this, and to illustrate what we have, it's the quantity negative 4 times itself 2 times because of the exponent of 2, and simplifying that, a negative times a negative is positive. 4 times 4 gives us 16. In this next problem, if we wanted negative 4 to the negative 2 power, it would have been in parentheses as the example above. This is shorthand for negative 1 times 4 to the negative 2 power, and it's only the negative 4 that is raised to the negative 2 power. To eliminate negative exponents here, it is only the 4 that drops to the denominator. So we have our negative 1 times 1 over 4 to the second power. We've eliminated the negative exponent by dropping that base to the denominator. Simplifying then, we have our negative 1 times 1 over 4 squared. 4 times 4 is 16. A negative times a positive is a negative, and 1 times anything is that anything. So our final simplified answer is negative 1/16, which we can write with the negative out in front. We also could write this with negative 1 in the numerator to show that it's a negative quantity, and for matter of fact, we could have 1 over negative 16, all of these being equivalent to the simplified version of this original quantity. This next example is a product of two things. The first variable has the negative exponent. Our directions were to express using positive exponents. So in place of a to the negative 7th, to make it positive, we drop it to the denominator. But it's being multiplied by b, which has a positive exponent, so we'll leave it alone. We've eliminated the negative exponents, but to simplify this, we'll multiply these two quantities together. Since it's understood that this variable has a denominator of 1, we can express it as a fraction, and then multiplying fractions together, we multiply numerators and we multiply denominators for the simplified equivalent expression to the given monomial that originally had a negative exponent in it.